Hello everyone. Welcome to our presentation on fundamentals of physics. Today, we'll be exploring the exciting topics of work, energy, and power. Over the next few slides, we'll break down these concepts and see how they relate to the world around us. I'm glad you're here, and I look forward to guiding you through this fascinating subject. Let's get started. Work is measured in joules, or J, and 1 joule is equal to 1 Newton meter. Now, for work to actually be done, the force applied must cause some displacement or movement in the object. If the object doesn't move at all, then no work is performed, no matter how much force you apply. So, in essence, work is about energy transfer. When you apply a force and that force causes the object to move in the same direction, energy is transferred. The key point here is that movement in the direction of the force is what counts as work. To put it simply, the formula we use is W equals F times D, where W is the work done, F is the force applied, and D is the distance the object moves. This relationship helps us quantify how much work is done in various physical situations, connecting force, movement, and energy transfer, core ideas that tie into the bigger picture of understanding energy and motion. Let's start by understanding that energy is essentially the capacity to do work. It's what allows us to move objects, power devices, and drive processes. Now, when we talk about energy, there are different types to consider. First, we have kinetic energy, which is the energy of motion. Any object that's moving, whether it's a rolling ball or a flowing river, possesses kinetic energy. The faster it moves, the more energy it has. Next, there's potential energy. This is stored energy based on an object's position or configuration. For example, a stretched rubber band or a raised weight has potential energy because of their position or shape, and that energy can be converted into motion or work later on. We also encounter electrical energy, which comes from moving charges, like electrons flowing through a wire. This is the energy we use to power our homes and devices. And lastly, nuclear energy, which originates from atomic reactions, either splitting atoms in nuclear power plants or combining them in the sun. It's a powerful form of energy that results from changes at the atomic level. All these forms show that energy is a fundamental concept that underpins how everything works in the physical world. It's a unifying theme that connects motion, position, and even atomic processes, helping us understand how different systems operate and interact. Let's talk about potential energy first. This is the stored energy an object has because of its position or state. For example, if you lift a ball up, it has potential energy due to its height. The formula we use is P equals m times g times h, which stands for mass, gravity, and height. This means the higher or more massive an object is, the more potential energy it stores. Now, moving on to kinetic energy. This is the energy of motion. Whenever something moves, it has kinetic energy. The formula for kinetic energy is Ke equals 1/2 times m times v squared. So, the faster an object moves, or the more massive it is, the greater its kinetic energy will be. Think about a moving car, a thrown ball, or flowing water. All of these possess kinetic energy. The key takeaway is that both the speed of an object and its mass directly influence how much kinetic energy it has. Connecting this to our overall theme, understanding these energy types helps us see how energy is stored, transferred, and converted in various real-world situations. Power is defined as the rate at which work is done, or energy is transferred over time. So when we talk about power, we're really focusing on how quickly something happens. The fundamental formula for power is P equals W divided by T here. P stands for power, W is the work done, and T is the time it takes to do that work. This means that if you do more work in less time, your power output is higher. Power is measured in watts, which is abbreviated as W. This unit is named after James Watt, the famous engineer and inventor who contributed significantly to the development of the steam engine. Recognizing this helps us appreciate how fundamental the concept of power is in various technologies and engineering fields. Understanding power helps us see how energy transfer occurs in real-world scenarios, whether it's a machine doing work or a person lifting weights. The key takeaway here is that power combines the concepts of work and time, giving us a way to measure how efficiently or quickly energy is being used or transferred. This ties back to the overall theme of understanding energy and work in practical applications. Questions. Let's explore. Now, this is the moment where we open the floor for any questions you might have. Remember, no question is too small or too big. Every question can lead to a deeper understanding. As we've seen throughout this presentation, exploring these ideas helps solidify our grasp of the overall theme. So, feel free to ask about anything that's been on your mind, or that you'd like me to clarify further. This is your chance to engage directly and make sure everything makes sense. Together, let's explore these concepts more thoroughly and ensure we leave with a clear understanding. Thank you for your attention, and I look forward to your questions.